Hi, in this video I'm going to talk about what is analysis of variance, in short known as ANOVA. I'll also talk about how is it related to linear regression. So analysis of variance, in short known as ANOVA, is used for comparing means between two or more groups. Okay, so the important thing here to note here is comparison of means. So let's say there are two samples, sample 1 and sample 2, having means mu1 and mu2. If you want to know if mu1 equal to mu2 or not, then you will be using ANOVA for that. Okay, and you can extend that to more number of groups. You can have mu1 equal to mu2 equal to mu3, which could be your null hypothesis, and the alternative hypothesis could be at least one of them is not equal to the others. Okay, so in such situations you can use ANOVA. Now you might wonder, how can we use the hypothesis testing in ANOVA? Well, ANOVA is some form of hypothesis testing. We are not going to use t-test for that, because for t-test we just can use two groups. For more than two groups, t-test cannot be used. So here we can use t-test and we can use ANOVA, but if the number of groups is more than two, then we certainly cannot use t-test. In that case, we'll have to go in for ANOVA. So in nutshell, we can say that ANOVA is something that can be used as a way of doing hypothesis testing when there are more than two groups. Okay. Okay. So first we'll see what is one-way ANOVA. And here is an example. We have this, the null hypothesis that the means are all same. Okay, so all population means are equal. So that's the null hypothesis. That means no treatment effect, no variation in means among the group. So what is treatment effect? Okay, this is a technical term that we need to know. So treatment effect is just that there is no effect of an independent variable, okay, or any factor or any treatment, to so to say. Okay, so in all types of statistical analysis, you must be knowing that there is a response, okay, or outcome. So this is the response, and there are so many factors that affects this response. We call them as treatments as well. Okay, so in ANOVA we actually talk about the different segments of the same population. Okay, and that itself is something known as treatment. Okay, so there's no treatment effect, as in there is no difference across these segments. Let's say there are 4 segments to this sample: segment 1, segment 2, segment 3, and segment 4. That means the property of this population is same across the sample. Okay, and one of the property could be mean, the other property could be something different. It could be standard deviation, it could be variance, or something else. So there is no variation of means among the groups. That's what we mean by saying that there is no treatment effect. The alternative hypothesis is that not all the population means are the same. Okay, which is to say at least one population mean is different. Okay, so if one of them is different, let's say if mu3 is not equal to mu2, then we cannot accept the null hypothesis in that case. It need not be the fact that all population means have to be different. It's just that if just one pair is different, then that rejects or that contradicts the null hypothesis. All right, so that has to be kept in mind. F distribution is an important distribution in the study of ANOVA. We will try to find out an F statistics and compare that with the F distribution and take the threshold value from there. Pretty much like the way we take T statistics, we compute T statistics, and then we look at the T distribution, and using a threshold we come to know whether something is significant, insignificant, and so on. So pretty much same, except the fact that we now will use F distribution instead of T distribution. F distribution is something that is applicable when we take the ratio of variances. Okay, and there are two types of variances that we'll be talking about. One is between variance and the second one is within variance. So if when we are taking the ratio of two different variances, the ratio itself will follow F distribution. Okay, so that something we'll keep it in mind. So the F test, it tests the hypothesis that the two variances are equal. Okay, so if F statistic will tend towards 1, in that case we'll see that the variances are same, and in that way we can analyze if the means are same or not, and we'll see how they're related. The variance is related to the mean comparison and so on. It's slightly confusing at the moment because normally we do not relate variance with mean, but ANOVA is one place where we take the help of variance to compare the average values or the means of two distributions. All right, so the F statistic will be close to 1 if the sample variances are equal. Okay, so here the between is similar to what is within, which is the null hypothesis, and in this case it is the alternative hypothesis is that they are different. Okay, but ultimately we want to compare the mean, not the standard deviation or the variance, but we'll make use of variance. Okay, and let's see, take an example. How do we calculate ANOVA using hand? We can of course use the software which can automate things for us, but we can do everything by hand. How do we do that? So in order to understand, we need to follow few steps, and we will follow some steps before understanding the entire thing. Okay, so have some patience to go through the different steps. So we'll get to the end point obviously, but before that we'll just go step by step. The first step what we'll do is that we will calculate the group means, and we will call that as y bar 1 dot. So we have observation, we have 4 treatment, that means segments. Okay, so segment is something that we were calling it as treatment. That means the data is from the same population, except the fact that the samples collected from these populations are different. So these are sample 1, sample 2, sample 3 and sample 4. So they basically so the idea here is whether the average or the mean of sample 1 and sample 2, sample 3 and sample 4, are they all the same, or at least one of them is different. So that's what the intention of using ANOVA. So that's what we will get to know by using ANOVA. So we'll take the first thing, what is known as group mean, by taking simply the average of all observations. So from y11 to y110, if you take the average, you'll get y bar 1 dot. Okay, so this is just the average within a group. Okay, so this is one group, right? If you take the group, that you will get the group mean. Similarly, you can get the group mean for treatment 2, treatment 3 and treatment 4. Okay, the formula is simple. You just take the average, right? That's what it is, and we denote it as y1 dot, y2 dot bar, y3 dot bar, y4 dot bar. Okay, now remember this is group mean. We will calculate more number of means, so the definition has to be very clear and not so confusing. So this is group means we have calculated. Okay, so we can also calculate the within group variances. The within group variances will be calculated by just taking these many observations within the same treatment. Okay, in that way you will calculate for treatment 1. Similarly, if you take for treatment 2, you can calculate the within group variance for treatment 2. Don't mix them up. Okay, just take one treatment or one segment at a time, and that we will call it as within group variance. So this is within group mean and this is within group variance. Okay, using this simple formula that we all know for means and variance. All right, now we will calculate the group mean and the between group variances and so on. So before that, just that is just a representation of how we calculate the sum of square, um, sum of or within sum of square, within variance. Okay, we just call it as SSW or SSE. Okay, it's the same formula. Okay, just the one that we just saw here. So it's just a more additional slide in which we have just shown you that this is what it is. You can just summarize this in this particular small expression. Okay, and we call that as SSW or SSE. So henceforth we will just use the short form. So this is W is for within, or we can call it as error, because it has some relationship with linear regression. So error is something that is basically known in the linear regression statistical modeling technique. So many times people use it as an error. And why is it an error? I'm sure if you are aware of what is linear regression, you can very well relate, but otherwise just leave it. We just take it as SSW. Okay, but SSW and SSE are just the same. Now we will calculate what is the sum of the squares between group variance. Okay, so the overall mean for the 40 observations. Okay, we have 40 observations, right? 10 each. So 10 into 4 groups, and 10 observations in each sample. So the grand mean we will denote it as y double bar, and we have 2 dots to it. Okay, and this expression we will calculate. So we take all 40 observations, we add them up and take the average by 40, right? That's is the overall mean or the grand mean. All right, the sum of the sum of squares between, that means the variance between variance, can be calculated like this. You take the individual or rather the sample mean minus the grand mean. Okay, and take the square and sum it across the all segments. Okay, now we have this treatment side, this 4 treatments, and each treatment has a mean, right? Y1 dot, Y2 dot bar, Y3 dot bar, Y4 dot bar, right? There are 4 means, right? And then you take these 4 means to calculate the grand mean, right? There you take the variance. Okay, and then multiply with 10, because there are 10 observations, and we call that as SSB. Okay, sum of squares between, or the between variability. Okay, in short. Okay, so here is this short form. So we just generalize this. The total sum of square is another term. So here we calculate the variability across all samples, all 40 samples. Previously we were just doing it for let's say the first segment, and not the first segment, it's the 4 segments, and then we went ahead with the variability within the different means, and now the variability within all 40 observations. If I go back, in fact it's very easy to understand from there rather than taking in different slides. Okay, here we can see. So there are 3 variances we have discussed, right, so far. So I can explain it very easily. The first variance is the variance within each group. Okay, so here we'll have one variance, here we'll have one variance, here we'll have one variance. So that is nothing but your SSW. Okay, so variance in each segment. Then we have SSB, the variance for each of these means. So there are 4 means, right? Y1 dot, Y2 dot, Y3 dot, and Y4 dot. So there is a variance within these 4 observations, right? So that variance is your nothing but SSB. Okay, and the third one is total sum of square, TSS. So TSS is nothing but the variance of all 40 observations taken together. Okay, without segmenting them. Okay, hope it's clear, right? So this is within a segment, this is variation for the 4 means that we have calculated, and this is the variation in all 40 observations, right? So once these three, variations are calculated, we can just, put it them in a very simple formula. So we call that as partitioning of variance. Okay. So SSW and SSB, when you add them up, you will get TSS. So TSS is something that we learned here, right? It's just the variation or the variance of entire 40 observations. So it intuitively what it means is that the variation among these 40 observations is sum of the variation within each segment or within each sample plus the variation within the means of each sample. If you add them up, you will simply get this total sum of square or total variation among all 40 samples. That's as simple as that. You can do it yourself also. If you do it yourself, I'm sure you will get this, uh, particular expression very verified very easily. You take the data and you can see it by yourself also. How is it related to ANOVA? Well, an ANOVA is just a, just an hypothesis testing where we calculate the F statistics. I told you, right, a couple of slides ago. So in order to calculate the F statistics, we need what is SSB and SSW value for a given sample or for a given set of samples. We have 4 groups here. You can have as many groups as you want, okay, because no matter how many groups you have, you can have a single SSB and single SSW. Once you have that, okay, take the degree of freedom also. Okay, so degree of freedom also you can calculate very easily. So take the degree of freedom and then just normalize that with the degree of freedom. So the way we normalize is just take the division of that. Okay, so it makes slight changes. Okay, some adjustment it does. Okay, so that's what is used for normalization, right? It does some slight adjustment, but we don't need to get into the details of why this normalization is done. So basically what we're trying to do is that we're trying to get a ratio of SSB to the SSW. Okay, so that's what F statistic is, and obviously it's normalized by the degree of freedom of respective variances. Okay, and then we get what is known as F statistic. We then look at the F distribution table and then compare with the threshold. Okay, so if you want it at a 95% confidence level, we want it at a 99% or 90%, depending on at what confidence level we want the statistic or the hypothesis testing to be performed. We accordingly go and see the table. Okay, so we look at the p-value accordingly. Most of the times we go in for 95%, okay, which is conservative and is good for use. All right, we'll take an example and we'll see. So here's this example. We have 4 treatments. So this is something to do with some length. Okay, so these are numbers. Last time we had y1, y2. So these are variables last time, but here we have a numerical value, so we can actually calculate it and see by ourselves. So here there are 4 treatments, and we will calculate the SSW, SSB, total sum of square and so on. Okay, and then we will calculate the F statistic and see its significance, and thereby we will see whether the null hypothesis is agreed upon or the alternative. So the null hypothesis in this case is that the mean of treatment 1 is equal to mean of treatment 2 is equal to mean of treatment 3 and is equal to mean of treatment 4. So mu1 equal to mu2 equal to mu3 equal to mu4. Okay, and the alternative is that at least one of them is not equal. It need not be the fact that all of them have to be not equal to each other. It's just that if one of them is different from the others 3, then that breaks the null hypothesis. So that's the idea here. We'll see that. So we will first calculate the SSW. And what is SSW? It is just the variation within each segment. So we'll calculate for treatment 1 separately, and then we'll calculate for treatment 2, similarly for treatment 3 and 4. So before that, we'll just calculate mean, right? Because to calculate variance, we need to calculate the mean first. So variance is nothing but the difference of each observation from the mean. That means how far the observation is from the mean, and then you take the square and you do that for each observation, and then sort of you add them up, okay, and then you get the SSW, right? So here you have, we also calculate the grand mean, which is 59.95. So we'll calculate SSB first. Sorry, I said we'll calculate SSW first. We have calculated SSB. SSB is very easy to calculate, right? You take the individual means and we have a grand mean. Take the variance. Easy, right? There are 4 observations and just one grand mean. Take the variance is just the how far each mean of these 4 treatments is different from the, or how far they are from the grand mean, okay? And that's what is given by the SSB. Then we will calculate the SSW, which will be slightly more intensive calculation. That means we are calculating the SSW, which is summation of the variation within each group. So we'll take the mean and then calculate variance for each of these observations within a mean. We'll do that for treatment 2, treatment 3, treatment 4, and then we'll finally add them up. Okay, just go back and see the formula. You can easily do that, right? Slightly more complicated because we have 40 observations, so each time here you'll have to do it many times, here you have to do many times, and then add them up. The final one would be to do the TSS, but we don't need TSS here, okay, because we have calculated both, and if you just add them up you will get the TSS, because that's the formula. TSS is nothing but your SSW plus SSB, so you don't need to calculate TSS separately. You just either add them up. In fact, for ANOVA you don't need TSS because just the ratio of SSB and SSW, that's what is important, and once you have these numbers we can just go ahead in finding out the F values. So we have this ANOVA table. We have degree of freedom, sum of squares, mean sum of squares, F statistics, and the corresponding P statistics. Okay, so this is all done, and that we have the between variances and the within variances. That means this is SSB, this is SSW. You take okay, so you take the summation of that. Okay, I'm sorry, I guess I said the F statistic formula wrongly. Okay, just now you go back to the actual formula. That is the correct one. I think messed up. Okay, so I'm sorry for that. So you need to calculate the total. Obviously you just add them up and you get the total. Okay, and the you calculate the F statistic then. So how do you calculate the F statistics? F statistics is, okay, if I go back just to confirm if we're doing it correctly or not. Okay, let's go back and see whether we are doing it correctly. Okay, so the F statistic, which is normalized by the corresponding W degrees of freedom, is nothing but SSB divided by SSW. So perfect. I think we haven't made any mistake. Anyway, just follow this formula, and when you use this formula to calculate, given that we have now SSB, SSW, and TSS, you get the F statistics to be 1.14, and the corresponding p value, when you look at the F table, just go to and see the F table, take the value corresponding to 1.14 at 95% confidence. Okay, you will get the p value, the corresponding p value is 0.3. Does that mean that they are different? I mean, does that mean it's significant? No, it is not significant. In that case, we will accept the null hypothesis. So the null hypothesis is that W mu1 equal to mu2 equal to mu3 equal to mu4. We'll accept that. Okay. Otherwise, imagine the p value would have been 0.001. In that case, we would have to reject this null hypothesis. But in this case, we'll have to accept this. Okay, we can do more with ANOVA. Okay, not just hypothesis testing, just to see whether the means are same. We can also do more than that. So what are the things that we can do? We can also calculate something similar to what we see in linear regression, the R square. Okay, is the degree or the extent to which the variability in the response variable is explained by different factors or different segments, so to say. Okay, so the question here is how much of the variance in height is explained by the treatment group. So I told you, right, we are basically discussing here about height of someone. How is it explained by the treatment group? So how does treatment group, if you take this as a some kind of a segmentation, how much does that contribute towards the variation in height? Okay, that you can calculate by calculating the R square, which is just divide SSB with TSS, and you will get 9%, and that's what. So 9% in the variation in height is being explained by the different segmentation, because different variation. Okay, that's not much. 9% is certainly not much, but that's the in fact the reason why we concluded that the means are pretty much the same. That means there's hardly any different in the mean. Okay, and that's what is clear now statistically. It has a lot of uses. In fact, ANOVA is very useful in design of experiments, and in many areas where you have multiple groups and you want to test whether the average value of these groups are same or different. Okay, we just define what is known as a coefficient of determination, which is given by R squares, which is the SSB divided by SSB plus SSB, which is SST. Okay, SST means just nothing but the TSS, same. Okay, so SSB divided by the TSS, total sum of square, is what is known as the R square. Okay, which we can explain by this: the amount of variation in the outcome variable, dependent variable, that is explained by the predictor or the independent variable. Something that we also use in linear regression, right? Similar.